Thank you, Janusz and Andre, for inviting me. So I'll be talking about subset sums, some classical problems in what was, as Janusz said, additive number theory, and now called additive combinatorics. This is based on joint work with David Conlin, who's a professor at Caltech, and Huy Pham, who is just finished up his first year of his PhD at Stanford with me. I was hoping to have the paper available for you today. It's basically done. There's just some slight editing, and so it'll be available very soon. We'll put it on archive. Okay. So subset sums, slide subset sums in number theory. Yes, okay. Subset sums are very classical problems in number theory. Some famous problems along these lines include the Goldbach's conjecture that every even integer.
Sorry, Jacob, I don't think the slides have moved since the title slide for us.
Okay.
Now it is.
Do you see Goldbach's conjecture?
Yes.
Yes. Okay, good. Okay, so there's some delay here. Right, so Goldbach's conjecture says that every even integer, at least 4, is the sum of 2 primes. So you're representing every sufficiently large integer as the sum of 2 elements from a special sparse sequence, the primes in this instance. And this is Goldbach's letter to Euler, where he first starts discussing these types of questions. You have this? Maybe you see this?
Which we don't see.
You see this? Okay. So that means there's some delay. Do you see it now? No?
Not yet.
Not yet. Okay. That's unfortunate.
But we can remember your words.
Now you see it. Okay. So it looks like there's a little lag here. Okay. So there are other problems in number theory of this sort. A famous example is Gauss's Eureka theorem, that every positive integer is the sum of 3 triangular numbers. And this was conjectured by Fermat much earlier. And this is the page from Gauss's diary where he writes Eureka, number equals triangle plus triangle plus triangle. And there are many other famous theorems of this sort. There's Lagrange's 4-square theorem, Hilbert-Waring theorem. And in general, they're about representing sufficiently large integers as a subset sum from some special subsequence. In this case of Gauss's Eureka theorem, it's the triangular numbers. Okay, so right. So these examples that I've discussed, which are very old, are all about representing sufficiently large integers by a small number of elements from these special subsequences. And there's still many problems which do not restrict the number of elements you need to use in the sum. So these are sort of the types of questions we'll be mainly studying. It's not the few size representation. We won't care as much about the number of terms used. So you see get the page from Gauss's diary here.
Yes.
Okay, great. Okay, so as I said, we're going to talk about representing sufficiently large integers as a subset sum from special subsequences. So let A be a set or sequence of positive integers. And sigma of A will denote the set of numbers which can be written as a sum of elements of a subset of A. This is area. The set A is called complete if every sufficiently large integer is in sigma. And it's entirely complete every positive integer is in sigma of A. So that's the difference between complete and entirely complete, is that you only guarantee that every sufficiently large, where entirely you want to represent all of the positive integers. And some examples include the powers of 2 is entirely complete because we can present every positive integer in base. However, this is quite fragile. If you delete any element from the sequence of 2, you're not complete anymore. In fact, you'll be representing about half the positive integers at that point. So now another interesting result in this area is that powers is complete. You can represent every sufficiently large positive integer as a sum of perfect kth powers and distinct perfect kth powers. And one might think that this already follows from the Hilbert-Waring theorem, but there's a small distinction here that in Sprague's result, you only are allowed to add distinct elements, whereas in the Hilbert-Waring theorem, you're allowed to use the same power more than once. Birch in the late 50s proved that if P and Q are co-prime positive integers that are at least 2, then the numbers which can be represented as a power of P times a power of Q is a form a complete sequence. That's an interesting example. And as an example of a dense sequence which is not complete is the set of numbers. Modularity reasons is a good reason why sometimes you don't have complete sequences. So we saw a couple natural reasons why a sequence might not be complete is it fails to satisfy some modularity constraint, or that the sequence is sufficiently sparse. Okay. Now, entirely complete sequences, so you can see the side entirely complete sequences?
Yeah, it's good.
Yes.
Okay. Yes. So entirely complete sequences have a nice characterization, and this is due to Ron. It's very simple. If you have a set of positive integers, it's entirely complete if and only if it contains the element 1, and it doesn't grow too quickly, in that if you take the kth smallest element and subtract 1, it's at most the sum of the smaller terms. This is pretty easy to prove. To prove one direction, if ak minus 1 is greater than the sum of the smaller terms, then there's no way you can represent ak minus 1 as a subset sum from A. You'd either have to use smaller elements, but then they don't add up large enough, or you have to add up larger elements and then you end up getting too much. And in the other direction, you can show inductively that the sum of these first k terms, the entire elements from 1 to the sum of all the elements up to the kth element. And this is a simple proof by induction. When you add the next term, you get all the previous terms in that interval, plus you can shift them ak plus 1, and then you'll get 2 intervals that overlap and will be their union will be precisely the interval you're looking for. More generally, if you have a set A of integers that for which sigma of A contains all integers in the interval from x to x plus y, and if A is a positive integer, which is at most y, then if you add A to the set big A, then the subset sum will contain an even longer interval, which is the same interval, but you're just adding A to the, so it's plus A longer. And this is a nice way of building intervals in subset sums. Once you get a large enough one, you can bootstrap it in this way. So the simple lemma is a useful tool in this area. And you can iterate this, and that's just precisely what the second part of this lemma says. Okay, another area of study of this form is the complete polynomial sequences. which polynomial sequences are complete. So let's let P be a polynomial in one variable. For example, P could be P of x equals x cubed. And we're going to be the set of values of P where over the integers that are at least 1, so the positive integers. And we want to know if this sequence A is complete. Now, there's some basic properties such a sequence must satisfy. The leading coefficient of P should be positive. And the reason for that, if it's not positive, then there's only a finite number of terms which are non-negative from A. And the way you'll be able to represent all sufficiently large positive integer way. So that's one simple necessary condition. Another one is that for every prime P, so this is going to be a modularity condition, there is a positive integer n, so P does not divide the P of n, the polynomial P of n. And this is necessary because if every P of n is divisible by the prime P, then all the subset sums would also be divisible by P, and you wouldn't be able to represent all the sufficiently large positive integers. And it turns out these necessary conditions are sufficient, and this was proved by Roth and Sekresh in 1959 using an analytic proof. And there's a result of Castles from 3 years later, proved using the circle method that also you can deduce this result from. And then there's another characterization by Ron Graham, which is a little bit more useful and to use in practice. And it's a bit more general. If you have a polynomial, also his proof is elementary, which is nice. So if you have a polynomial P of x degree k, which is a real polynomial now, it's not necessarily integer coefficients, you can always write it as a sum of binomials in this form where you take a real number alpha sub I times x choose I. X choose I is this polynomial of degree I. And you can write P of x in this form. And then the sequence A, as above, is complete if and only if the leading coefficient alpha k, this is in the degree k term, the first one, is positive, and alpha k is a rational number when written in reduced form as P of k divided by qk, so pk and qk are integers, the numerators have greatest common divisor 1. So that's Graham's characterization. As we discussed before, this notion of completeness is quite fragile. You could, for example, for the powers of 2, just delete a single element and destroy the completeness property. So Burr and Erdös were interested in how robust is completeness as a notion, and can you come up with better notions in the sense of being less fragile than completeness? And so they came up with this idea of Ramsey complete sequences. So if we have a set or sequence A of n will denote the number of elements of A up to n. And this set or sequence A is called R Ramsey complete if no matter how you partition A into R subsets, every sufficiently large integer is in the union of the subset sums of the AIs. Now, this looks a little bit more complicated than it is, but actually the partition into R sets is the same thing as just saying you're coloring each of the elements of A with one of R colors, and you want to represent every sufficiently large integer as a monochromatic subset sum. So as the sum of elements that are the same color. Burr and Erdös proved that there's a 2 Ramsey complete set, A, with A of n equals big O of log n cubed. And their proof really relied on the fact that you were using 2 colors. They were unable to make a construction work like this for more than 2 colors. And their construction is using some variance on powers of 2, which you end up using more, and you add them together. They also showed that if A is too Ramsey complete, then it has to have at least log n squared elements up to n. Their proof of this is not in their paper. They said it's pretty challenging. So they proved a somewhat weaker result in the paper, but said it's possible to prove this result. And they asked several problems. One question they asked was to improve these bounds for two coloring. And then they wanted to show that there's a sparse R-Ramsey complete sequence for R bigger than 2. So they weren't able to prove this at the time, and determine which polynomial sequences are R-Ramsey complete. And in this work with Conlon and Pham, we solved these questions. Erdős later had offered some prizes for several of these questions. And so we prove a result which solves all of these problems at once. And so I'll explain what those results are. So our first theorem shows that there's an R-Ramsey complete sequence A with the number of elements up to n is on the order of log n squared, and even it's multiplied by r times a constant. And further, if A is R-Ramsey complete, then we come up with a simpler proof that A has to have at least some constant times r log n squared elements up to n for all sufficiently large n. We further generalized this to degree d polynomials. So what we showed is that if a degree d polynomial, the polynomial is complete, the sequence is complete, then there's actually a sparse subsequence. It's as sparse as possible, essentially, so that such that the sequence is R-Ramsey complete. So this simultaneously answers these questions. And as a corollary of this, polynomial sequence have some robustness. If you have a polynomial sequence which is complete, then it's R-Ramsey complete for all R. So that's just a corollary of this, because in fact, you'll be able to find a sparse subsequence which is R-Ramsey complete. Are there any questions, or can you see the slides well?
Yep.
Yes, okay, good. Okay, so I want to say a few things about the proofs. I want to first talk a little bit about the upper bound.
There are some questions in the chat also.
Okay. Let me try to go to the chat. Okay. So Shachar asked, why do you need to consider cup sigma of AI? Is there a counterexample to use sigma of AI for some I? That's a great question. I should have mentioned this. Yes, there is a counterexample. If you use, say, two colors, red and blue, and you color up to 2 to the 2 to the, between 2 to the 2 to the I and 2 to the 2 to the I plus 1, all of those elements, red if I is even, and blue otherwise, you can show that there will be elements that you can't represent monochromatically for each of the colors. So if you fix one of the colors, you can't represent all positive integers, all sufficiently large positive integers monochromatically. So you can't just restrict to one color class. That's a great question. And then there was another question, which is also a great question. Are these density or Ramsey results? And we started with coloring Ramsey results, but actually we're going to turn soon to some density type results that are related. So, so we can prove some density results. They're slightly different, and we'll see what those are shortly. Great. Okay. So for the proof of the theorem, there's a key lemma. which is a density type statement. But we'll get into some other density type statements soon. So if you have an epsilon that's between 0.5 and n is sufficiently large, there's going to be a subset of the interval from n to 2n. So this is a set of integers that's fairly sparse. It's only roughly log n size, and there's a factor of 1 over epsilon, such that for every subset of your set Sn that's at least an epsilon fraction of Sn, there's going to be a huge interval in the subset sum of A prime. And this huge interval goes from some number yn to 3yn, where yn is on the order of n times log n, and there's a constant factor in front. And the question is, how do we construct this set Sn? That's something important. But also, how does this imply theorem 1? And it's fairly simple to get theorem 1 from this key lemma. For each power of 2, n equals 2 to the I, and with epsilon equals 1 over r, we're going to let A be the union of s of 2 to the I for each of these i's. So we're going to have these subsets, and we're going to pick our sequence A to be the union of these subsets s sub 2 to the I, where we pick from the key lemma that this exists. Now, let's consider an R coloring of the set A, and let AI consist of the elements of the most common color from S2 to the I. The interval from y sub 2 to the I to 3 times y sub 2 to the I plus 1 covers, sorry, it should have been 3 times y 2 to the I, covers all large integers, so these intervals, and we know that I sub I is going to be a subset of sigma of AI by the key lemma. So the theorem 1 really boils down to this density type lemma, and so I'll try to indicate how you prove this key lemma. So how do we build the set S sub n? So in previous work, one would do it constructively. For those who love the probabilistic method and think this way, it's very natural to try to pick Sn to be a random set. And indeed, we pick it at random. Now, there should be some objections to just trying to pick it uniformly at random. And there's a very good objection. If you just pick Sn uniformly at random, half of the elements roughly from Sn will be even. And then if you let A prime be the even elements from Sn, you're not going to get an entire interval in sigma of A prime. So if a lot of the elements are even, you would run into a problem that you wouldn't be able to build an interval. You could build maybe multiples of 2, but certainly not the odd numbers in such circumstances. And similarly, you shouldn't have a large fraction of your elements be multiples of 3 or 5 or any other small prime. And so to avoid this circumstance, we're going to pick the set Sn at random, but from the elements that have no small prime factor. And there's some room to how you pick this. We picked it so that the elements of Sn have no prime factor less than log n over 2. So you can still show that the interval from n to 2n will, if n is large enough, will have many elements that have whose prime factors are larger than log n over 2, and you're going to be picking a random subset from there. What?
A random subset of primes, of just the primes between n and 2n will be okay?
In terms of the analysis, it's a little bit better to allow for some small elements. Probably that would work. But the way that we did the analysis, it's actually better to not pick just primes. But yes, probably one could analyze it a little bit differently, and that would work. one has to check the details of that. Now, what we prove is that with very high probability, a random A prime, which is a subset from n to 2n of size 4,000 log n, and each element has no prime factor less than log n over 2, satisfies that the entire interval from yn to 3yn is in the subset sum of A primes, in sigma of A primes. And then we union bound over all of the A prime, which is a subset of Sn. So this very high probability is really very high. And you can union bound over all of the subsets of your Sn. There's a general way that we build the interval that works for this problem and many other problems that we were working on. And so I want to discuss what this sort of recipe for constructing an interval is. Basically, what happens here is that you reveal the elements of A prime one at a time and see how much, as you add additional elements, does it increase the size of sigma of A prime. And so if you add an additional element to a set and you look at the sigma, it could double at most. And if sigma of of the current value of A prime, so some AI prime, which is the first I elements of A prime, if that's small, it's very likely that it will go up by a large factor when you add an additional element. So you can show there's a simple lemma that shows that it'll go up a lot, and you can use this to show this result about with very high probability. A random A prime will have this property. So in general, though, this is very helpful for building to showing that sigma of A prime is large, but it doesn't tell you get the whole interval. And so there's some other tools that are helpful for doing so. So here's a recipe for finding intervals and subset sums. So we're going to start with a set A of integers, and you'd like to show that sigma of A contains a large interval. Now, if A consisted entirely of even numbers or some multiple of D, then sigma of A certainly wouldn't contain a large interval. So if A or almost all of A are multiples of a given number D, you could throw out those few elements that aren't and divide out by D, and instead of getting an interval, you would end up creating something called the homogeneous arithmetic progression. So we won't worry about these modularity issues at this point, and assume that we've already thrown things out. So that no number D is a factor of almost all the elements of A. So the first thing is to partition A into L sets, A1 to AL, and one does this essentially equitably in this sort of general recipe. And then the main step is you partition AI into two sets, BI and CI, so that the set of subset sums of BI is large modulo each of the elements of CI. And using the previous step, you can show that sigma of A prime is going to be large. And again, here we'll explain this deduction of 3 from 2. And the fourth thing is using that each sigma of AI is large, we get that their sum set, and hence sigma of A contains a log interval. So I want to say a little bit about how we go from 2 to 3 and how we go from 3 to 4. To get 3 from 2, there's a very simple claim that turns out to be quite useful. If you have a positive integer C and a subset B of the integers, where C is not an element of B, and the size of sigma of A considered modulo C is at least H, so that sigma of A intersects at least H congruence classes modulo C, then when you add C to A, the subset sum goes up by at least H. And that's because if you look at those arithmetic progressions with common difference C, they're going to have to go up by at least 1 for each of the congruence classes. And so one will end up getting this inequality, and this is quite helpful from going from 2 to 3. In going from 3 to 4, there's a nice inequality of Lev, which tells you if you have L subsets of the integers. Each of the AIs are large and is a subset of an interval of at most q+1 elements. So each AI is a large subset of or rather dense subset of an interval, and none of these AIs is a subset of an arithmetic progression of common difference greater than 1. Then their sum set contains an interval that's quite long, of length at least L times n minus 1 plus 1. So using this recipe and some additional tools, you can build large intervals in subset sums, depending on the context. So this is sort of the general recipe that applies to a lot of the results that we're looking at here. Are there any questions about this? This is all rather vague, and but I'll get into some more detail soon of some results and of some other results that this applies to. Good. Right. So if for the results about polynomial sequences being Ramsey complete, there's some additional tool which is similar to how PET induction in the work on generalizations of Szemerédi's theorem to polynomial sequences, polynomial arithmetic regressions. So there was this question about what about density type results instead of coloring results. And this problem wasn't considered before our work, but it seemed very natural. So there are many results in Ramsey theory that are coloring results, and sometimes you can prove stronger density type results. For example, van der Waerden's theorem tells you that whenever you finitely color the positive integers, you have to have arbitrarily long monochromatic arithmetic regressions, and this follows from the stronger Szemerédi's theorem that every dense set of positive integers contains arbitrarily long arithmetic regressions. So we want a similar result for Ramsey completeness, and the natural notion for this is to call a set A epsilon complete if every subsequence of it, so you think, or this is a set, subset of it, which has at least an epsilon fraction of the elements up to n for sufficiently large n, is complete. So the natural question here is, how sparse can an epsilon complete sequence be? Now, one thing that might throw you off a little bit is why should there even be any set which is epsilon complete? If you look at all the positive integers, you look at the subset, which is the even positive integers, that's not complete, and yet it has density a half. So the thing is that this notion of completeness is not monotone. And if you take A to be, for example, the set of primes, you can use results of Szemerédi-Vu to show that it'll be complete. That the primes are epsilon complete for any epsilon greater than 0. So here A is going to be an infinite set of positive integers. And we want to know how sparse can an epsilon complete sequence be. And an epsilon complete sequence A must satisfy some natural conditions. They must satisfy a modularity and a growth condition. For each prime P, the multiples of P and A have density at most epsilon. And this is exactly why we can't take the set of all positive integers, because, for example, if P is 2, the density of the multiples of 2 would be a half in this case. So A should look prime-like in the sense of having, for each prime, few elements, relatively few elements that are multiples of that prime. And there's a growth condition, which is that there's some positive constant C such that the kth element in the sequence, when you write them in increasing order, is at most the sum of the elements, the first epsilon k plus C elements for all k. And if this doesn't happen, you can show that it's not going to be epsilon complete by taking a large interval, then skipping a huge amount later, and then taking another large interval and continuing this sort of process. you can show that you will be able to find a subsequence which contains at least an epsilon fraction, which will not be complete. It looks like there might be a question. Is that right? So there's a question about, is the density less than epsilon or just not more? It should have density at most epsilon. If it was certainly bigger than epsilon, it wouldn't work, and you have to be careful around epsilon. So this is not entirely precise. Certainly, it's so if you say it's less than epsilon, it should be at most epsilon. Right, and what we prove is that roughly a random sequence satisfying these two conditions, so it has to have some growth condition and some modularity condition, is almost surely epsilon complete. And in particular, consider a set of integers constructed, a sequence of integers constructed recursively. Start off with any initial sequence f1 to ft, and fm will be defined to be the sum of the of fi, where I is at most epsilon m, for larger for m being bigger than t. And then if a is epsilon complete, we prove that ak would have to be big O of f sub k. So if you start off with any initial sequence f1 to ft, the growth of this sequence will be within a constant factor, depending on the initial terms, of any other such sequence. And what we show is that if a is epsilon complete, then it can't grow faster than this sequence of this f sequence. And there exists an epsilon complete sequence which grows exactly as fast as this sequence. So within a constant factor. I just want to, before moving on, so we talked about coloring and density results for completeness. Before moving on, I want to just mention a couple conjectures. Here's one that's still open about completeness. If we have pairwise relatively prime positive integers, p1 to pr plus 1, and they're all bigger than 1, then the sequence p1 to the i1, the sequence of elements which are powers of p1 times powers of p2 all the way up to powers of pr plus 1 is Ramsey R complete. And in the example r equals 1, this is precisely Birch's theorem. And this is a natural generalization of Birch's theorem. This sequence is not going to be r plus 1 Ramsey complete. And you can show this by a simple coloring. You're going to assign a particular element from the sequence color j, for which the exponent ij is non-zero and j is at most r, and color r plus 1 otherwise. So if an element in your sequence has a power bigger than 0 for one of the first r terms, then it gets one of the first r colors. And otherwise, it's going to be a power of pr plus 1, and then you give it color r plus 1. And you can show that the elements of color j for j at most r are all going to be multiples of pj, and there's still going to be a lot of uncolored elements from using just the first r colors. But the elements of color r plus 1, the elements of color r plus 1, their subset sum, because it's such a sparse sequence, their subset sum is going to be very sparse and won't be able to cover the remaining elements that aren't covered by the earlier ones. So that's how you can show that. Okay, so I want to move from trying to guarantee all sufficiently large positive integers in your subset sum to guaranteeing a particular element. And this is also a very well studied area of questions. This particular question that we're going to look at next is due to Paul Erdős. He made the following definition: let f of n be the minimum r such that there is an r coloring of the first n-1 positive integer, such that no monochromatic subset sums to n. So let's see an example of this. So f of 23 is at most 3. And do you all see this coloring of the first 22 positive integers with colors red, blue, and green?
Yeah.
Yes? Okay, good. Okay, so the first 6 positive integers are colored red in this coloring. And if you add them all up, you get to 21, which is less than 23. So there's no way you're going to be able to add up to 23 using red elements. Now, the elements that are green are bigger than 23 divided by 2. So if you add any 2 of them up, you're going to get an element you're going to get a sum that's bigger than 23. So there's no way you can represent 23 as a sum of 2 green elements. And if you add up any 2 blue elements, you're going to get a number that's less than 23. And if you add up any 3 elements that are blue, you're going to get a number that's bigger than 23. So there's no way to add up blue elements to get exactly 23. And one way of creating this coloring is to color greedily. Just start with 1 and 2 and 3, color all of them red until you can't anymore, and keep coloring, trying to, in a way that avoids the desired number as a monochromatic subset sum. Now, this is one way to color. It's not an optimal way to color, but this sort of greedy coloring, you can check. It's an exercise. We'll use roughly square root of n over 2 colors asymptotically. But this is not close to optimal, and Erdős was able to show that f of n is little o n to the 1/3, and he asked if the exponent 1/3 is tight. So does it grow like cube root of n, the number of colors you need to color the elements from 1 to n-1, so that n is not a monochromatic subset sum. At that time, when he first introduced the problem, he wasn't able to show f of n is at least n to the epsilon for any fixed epsilon, and he thought that would already be interesting. Now, later, Noga Alon and Paul Erdős were able to prove this, or settle Erdős's question in the positive, and they showed that the number of colors you need is roughly n to the 1/3. Except there's some additional logarithmic factors in the lower and upper bound. And they conjectured that f of n grows more like this upper bound, so that it's like n to the 1/3 divided by log n to the 1/3, roughly, more rather than the lower bound, which is n to the 1/3 divided by log n to the 4/3. Vu, using earlier work using some earlier joint work with Szemerédi, improved the lower bound to n to the 1/3 divided by log n, but they're still off by the number of logarithmic factors here. With David Conlon and Huy Pham, we determined actually what this number of colors is up to an absolute constant factor. And indeed, it's closer to the upper bound in that the number of log factors is in fact 1/3, as it is in the Alon-Erdős bound. But if you start going into the log n factors, things look a little bit different. If you see this bound, there's a factor in the numerator of n divided by this Euler-Toten function, phi of n, that's the number of elements up to n, which are relatively prime with n. And n over phi of n is always going to be greater than 1, but at most log n. And for most integers, n over phi of n is going to look like a constant, in which case this improves on the Alon-Erdős bound by a log n factor. However, if n is highly divisible by small primes, n over phi of n is going to look like log n, in which case the Alon-Erdős bound is tight for such n. So in the rare case that n is very divisible by small prime factors. Another interesting thing about this bound is that it shows that f of n is not monotone. That if you take a value of n, which is highly divisible by small primes, and you pick a prime nearby as a different value of n, that f of n can fluctuate by a factor log n pretty quickly. And so locally, it has some substantial fluctuations if you think of log n as substantial. It depends on whether you think of log n as substantial or not. So I want to tell you about where does this Alon-Erdős coloring come from that improves on this simple greedy coloring earlier, and then how can you get this extra more careful, which it turns out to be correct up to a constant factor bound. So the Alon-Erdős coloring makes use of several nice observations about sets that don't have n as a subset sum. So the first thing they do is they use, so we're going to set R to be the number of colorings that we're going to use in this coloring. And so this is in the Alon-Erdős bound, and there's different types of colors in their coloring. The first type of coloring, so you're going to use half your colors to color the integers between n over j plus 1 and n over j. You're going to color it with color j. Are the slides not moving ahead? Do you not see type 1 here?
We do see. I do see.
We do see. Okay. Okay. There was a question about this in the chat. Okay. So right. So if you have this interval of integers between n over j plus 1 and n over j, if you add up any j of those elements, you're going to get less than n. But if you add up any j plus 1 elements, you're going to get something that's larger than n. And so there's going to be no way that you're going to add up a bunch of positive integers from this interval in order to get exactly n. So that's one way. And that colors all the big positive integers. So anything bigger than 2n over r is going to be colored by elements of type 1. So that covers most of the integers, but there's still a lot of small ones left. Now, there's also modularity things that you can use, and this is what type 2 does. If you look at the first r over 4 primes p that do not divide n, we can color the multiples of p using one color. So for example, if n is 23, we could take all the even numbers and use that as a color, and any subset sum would not add up to that number n, which was 23, because any subset sum would be even. And so at this point, we've used three r over 4 colors, and we still have r over 4 colors left. Now, using some basic number theoretic estimates, you can check that there's not so many integers that are left over, and they're all fairly small. So you can group the remaining uncolored elements into r over 4 color classes, each with some less than n. If you do this carefully, you can pick r to be precisely the value that we have in the theorem. Okay. So any questions about this? So there are 3 different types of colors that come into their coloring, and it turns out that you want to do roughly the same thing to get the optimal coloring, but do something extra in type 3. So you split up the type 3 colors in a different way, and we'll explain what that is in the new coloring. So as an example, you can just see that if we wanted to get f of 39, we see it's at least 4. We can color the interval 20 to 38 with one color, 13 to 19 with another color. The even elements that are less than 13 will be of type 2, and the remaining elements, they add up to something less than n in this case, and they'll be of type 3. Okay. Good. So I want to tell you what the new variant of this is, which gives you the optimal bound. We're going to pick an integer d that's maximum such that d and n are relatively prime, and phi of d is less than r over 16. Then for each unit mod d, t, we're going to let xt be the integer from 1 to d that's the multiplicative inverse of T modulo D. Now, if you have a sum of elements AI that are each T mod D, and there's S of them, and they add up to N, then S must be congruent to X sub T mod D. That's not correct. It's there's a multiple here that I'm missing, which is N. S must be congruent to NXT mod D. Sorry. And then how are we going to color the remaining elements that aren't of type 1 or type 2? We're going to color those elements that are, so if S is going to be congruent to XT mod D or NXT mod D, then it's either going to be between 1 and D, between D and 2D, or it's going to be larger. And you're going to use one color class to get the elements that are bigger than N over, sorry, I should have put XT to be NT inverse mod D, not T inverse mod D. Then the rest of the slide is correct. So X sub T should be N times T inverse mod D. And one color class we're going to use are those elements that are T mod D that are bigger than N, that are at least N over X sub T. And then you would have to use at least X sub T elements because of the modularity reason to add up to N, but then they're too big. So that color class won't work. So for each T, you're going to pick one color class like that. And one for those that are congruent to T mod D with A between N over X sub T plus D and N over X sub T. And again, you're going to have to use at least X sub T of these. You're going to have to use more than X sub T plus D of these elements. And it's going to end up being too large. And finally, there's not so many remaining elements. And they're also pretty small. So the uncolored remaining elements are going to be less than N over D. And you're going to group them into size D color classes. And if you optimize all of this, you get this precise number of colors, which is tight up to a constant factor. Okay, so it's a pretty intricate coloring. And it may be surprising that this is actually optimal up to a constant factor. That's the case, and the reason why we're able to prove that is because of these ways of building intervals and subset sums. They're pretty robust ideas, and you can add them to additional things like the Selberg sieve to get the bound in the other direction. Okay, so a natural generalization which had not been studied before, but comes up naturally is, instead of trying to get the monochromatic subset sum to add up to M, to N, let's have it add up to M. And the possible values of M that make sense are between N and N choose 2, based on the fact that it's not interesting if M's smaller than N. And if you sum all the elements from 1 to N minus 1, you get N choose 2. So there's no way you'd be able to get it as a monochromatic subset sum if M is bigger than N choose 2. So those are the M that this problem is interesting for. We end up proving a tight bound for this. And what happens is that it looks like the previous coloring in a certain range of M, if M's not too large, and then it switches to a different type of coloring that works, that's optimal. And there's some other function rho of NM, which you can describe, which is tight. And this rho of NM has to do with the primorial. So the primorial function, K sharp, is the product of the first K primes. And we're going to let rho of NM be the smallest positive integer such that rho divided by tau rho M is at least n squared divided by phi of M. And here tau of rho M is n divided by phi of n, where big N here is rho sharp times M. So it's a little bit long to explain what this function is, but you can write it down and actually describe what it looks like. And one can generalize the previous result to this. Okay, so we've talked about complete sequences, and we talked about density complete. So we went from Ramsey complete and density complete. That's the coloring results and extremal results for completeness. Here we've talked about the coloring result for a single monochromatic sum, for a single sum. And it's also been well studied. The extremal problem for this has also been well studied. So you want to find how large of a subset from 1 to n can you find so that no subset sum adds up to m. And this was first introduced by Erdös and Graham. So let G and m be the maximum size of a subset of 1 to n, where m is not in sigma of a. Let SNDM be the smallest non-divisor of m. A natural construction of a set A with m not in sigma of A is to take all of the multiples of this number SNDM, the smallest non-divisor of m, because any subset sum of the multiples of SNDM would have to be a multiple of SNDM, and therefore could not be equal to m. So Noga alone proved that GNM is within an absolute constant factor of this construction I just mentioned for a wide range of m. So then later with Freiman, they did a more careful study and even precisely determined what GNM is in a certain range. So let SNM be the floor of n over SNDM, which is precisely the size of the set of multiples of SNDM. But then they're able to add SNDM minus 2 to that. And what they showed is that GNM is at least this SNM by considering the set consisting of the multiples of SNDM together with some additional elements, which are each plus or minus 1 modulo SNDM. And you have to pick the plus or minus 1 carefully in order so that it doesn't, so that you can't represent m as a sum of elements from A. So Alon and Freiman proved that that these two functions are equal in a certain range when m is very large, at least n to the 5/3. But it's impressive that they get the exact sharp result here. And Alon conjectured that GNM is asymptotic to SNM in the larger range from exponent 1 to 2. And this was eventually proved by Tran, Vu, and Wood, this asymptotic formula. What we were able to prove using these same tools, and an additional tool which I'll mention soon, is that this lower bound turns out to be tight in a very large range from n over log n to n squared over a constant times log n squared. And then a different construction takes over, which is even simpler. If you just take an initial interval of length smaller than square root of 2m, that set of integers can't add up to m because they sum up to something less than m. And that construction is asymptotically tight if m is fairly close to quadratic in n. And so the optimal construction switches from this modularity construction to a sort of like a growth construction when m gets close to n squared, which shows that these two sorts of conditions come in all over the place in these sorts of problems, that these modularity conditions are important and size conditions, growth conditions are important. To do this, we reduce this to another problem that's been well studied about long arithmetic progressions in subset sums. There was a long-standing conjecture of Erdős and Folkman, which was solved by Szemerédi and Vu in 2006. And what they proved is that if you have a subset of the first n positive integers, a, and it has at least size, it has size at least some big constant times root n, then sigma of a, the set of subset sums, contains, sorry, it's supposed to be an n-term arithmetic progression, not, there shouldn't be an h here. It should just say AP. And so AP is short for arithmetic progression. So in arithmetic progression in general, so the results about arithmetic progression and not homogeneous arithmetic progressions. And arithmetic progression, AP, which is written out a plus d, all the way up to a plus k minus 1 times d. So here a is the first term, d is the common difference, and k is the number of terms. It's called homogeneous. An arithmetic progression is homogeneous if d, the common difference, is a divisor of the first term. And it turns out for many problems in this area, it's really helpful if you can find a homogeneous arithmetic progression that's long. Along these lines, Freiman and Sárközy proved independently that if you have a subset of 1 to n that has size at least a constant times root n log n, then sigma of a contains an n-term homogeneous arithmetic progression. So the Szemerédi-Vu result is weaker in the sense that they only produce an arithmetic progression and not a homogeneous arithmetic progression, but it's stronger in that they don't have the logarithmic factor. So these results are incomparable. And it was asked by Sárközy and later by Tran, Vu, and Wood if there's a common generalization of both of these, a strengthening where you can remove the log n factor and still get a homogeneous arithmetic progression. And using the tools that we mentioned earlier, you can prove that sigma of a, and a few small additional ideas, you can prove that sigma of a indeed will contain an n-term homogeneous arithmetic progression. So this conjecture of Sárközy and Tran, Vu, and Wood holds, and these results have a common strengthening. And it turns out that this previous work of Freiman and Sárközy found many applications in additive number theory. A later paper of Sárközy mentions many of them. And this new result allows you to improve on some of these just because you have a stronger thing that you're black boxing into these results. Okay, so I think I'll finish here. Thank you very much.
Thank you, Jacob, for the wonderful talk. Many results, more than I can digest at one sitting, but they are clever people. So any more questions?
So what goes into this proof of the last theorem, if you can mention it in a couple of words?
So unfortunately, it's a little bit longer than I want to get into detail about, but one of the first things that's important is if your set A is almost all multiples of a small divisor, you throw out those elements that aren't that small divisor and factor out by that small divisor. And in this way, you make sure that the remaining set you get isn't almost entirely multiples of a same number, in which case you wouldn't be able, it's kind of hard to work with. So then once you do that reduction, you're trying to build an interval in sigma of a. And this recipe from earlier is very important in doing this. So these tools that I mentioned earlier play a fundamental role, and there's some additional work to make everything work out. In some of the applications, actually, you want something a little bit stronger. So this is a corollary of a stronger theorem, which tells you how many terms you need in order to make the various elements in this homogeneous arithmetic progression. So there's a little bit more. It tells you what based on the set A, it tells you what the common difference D is. using this sort of technique. And I don't want to bore you with too many details in the few minutes we have left. So I'll stick with that, and the paper will be available very soon.
Okay, thanks.
Any other questions?
Question, can you hear me?
Yes.
Yeah, Jacob, thank you, very nice talk. Going back to the early part, instead of epsilon being fixed, I mean, suppose you take, say, the primes, as Noga suggested. Can you say that any sparse subset of them will be a complete set, where sparse is not just for a fixed epsilon, but in terms of the number of elements up to n?
Right. So you can prove that even down to roughly square root of n for the prime. So up to n, if you have used just from Szemerédi-Vu, you can use that already to get, if you have square root of n roughly, that you can get, so square root of n over epsilon roughly. Primes, a sequence of primes that's that sparse, then it will have that property. But if you really want a sparse one, something I should have mentioned here is that what's the growth of f sub k, or up to n, how many elements do you actually have in the sparsest sequence? And if you, in the Ramsey result, it was log n squared roughly. Here it's still n to the little o1, but it's closer to e to the root log n type behavior. And we can say more precisely what that is, but it has to do with this recurrence. Fm is the sum of the fi's where I is at most epsilon m.
Okay.
If it was, what?
Thank you.
Yeah. So it might be the case that there's primes, a prime sequence that is that sparse. But our proof takes elements which don't have small prime factors, and it really uses that. So it's not quite the primes, but it doesn't. It's just elements that don't have small prime factors.
Yeah.
I would like to ask the following. In the introduction, you mentioned that the set of all the values of a proper polynomial is complete. And I would like to ask if you allow yourself to use the same term several times. Can you bound the number of required terms for each n, like 4 squares in Lagrange 4-square theorem?
Yeah, so these analytic proofs of the Hilbert-Waring theorem can be modified to prove that. I think if you're allowed to repeat, and probably if you're more careful, you can get it to work if you only allow distinct elements. But the techniques we use here in these proofs really need a lot of elements. So often it'll be log n elements to get an element to guarantee an integer n, and rather than some constant number. And so these techniques seem to be pretty separate from the techniques that were used in the work of Hilbert and Waring, the Hilbert-Waring theorem proof.
Okay, thank you.
Other questions?
So do you use the log n elements because of the concentration later on? Or this union bound later on? Or?
So often, so as an example for the Ramsey completeness, we kind of look at how big, if we use any of the first I elements, how big sigma of AI is. If we use the first I elements. And so when we add an additional element, it tends to double the number of elements we're using. or go up by at least some constant factor. And to really get everything in an interval from, say, some number to twice that number, you really need to use logarithmically many elements to guarantee that. So it has to do sort of with these growth conditions that come into the proofs.
Any other question? Well, if not, then thank you very much, Jacob, and congratulations for the nice result. I wonder if there is any other result or conjecture in this circle of problems for which Erdős offered money, which you can still get, or you, this 350 was really the local maximum.
So for Ramsey complete, these were all the questions that we found of that they had studied. But we offer two additional ones. So I think these are interesting questions. We mentioned this conjecture we have that if you take r+1 relatively prime positive integers that are distinct, and you take the product of their powers, that they should be Ramsey R complete. And we know it's not Ramsey R+1 complete. That's one question. Another question I failed to mention, but I'll mention here, is these results about Ramsey completeness really use that we're taking a random subset. So this theorem that there exists an R Ramsey complete sequence A, it really uses randomness. And I don't know how to construct a set that's not random, that is so sparse. The Burr Erdös result for two colors, which has a weaker bound, is quite constructive. And this is very random, and I don't know of a construction. I think that's an interesting question, is to actually construct these things that are so sparse.